Hi, this video is about the load shear bending diagram again. However, this is something absolutely new, load shear bending. We are no longer working on using analytical approach. We're going to look at a graphical approach. So graphical approach has a bunch of rules. So in order to implement this topic, I will go ahead write down those rules first, and then we're going to use the 3 examples we did for analytical, and then using this brand new graphical approach to redo them, and we should get the same answer, right? So the first rule, I'm writing it down, is at concentrated load. So if you have a concentrated load, what happened to the shear force? So shear gonna goes in the same direction of the concentrated load. So example, if this concentrated load is downward, that means the shear is going to go downward, okay? So the second rule is if this load is distributed load, which we have seen some example for that in the last video. And here is a little trick or a little pattern we'll notice. It's a slope of the shear. The slope of the shear equals the distributed load intensity. That often was reading as omega x, right? So if we were writing this, because we understand the slope means derivative, so we can actually write this as the slope of the shear, which is dv over dx. That's our slope of the shear. That's gonna be equals this load intensity omega, and this omega is gonna be a unit of Newton per meter, for example. All right, so move on to the third rule. We'll have, you already kind of noticed last time, the slope of bending moment, that's gonna be equals shear. We have concluded that our last video with this discovery. So it's going to be equal to the slope of the bending. Again, the slope means what? Derivative. So that means slope of the bending, dm over dx. That's going to be equal to your v. Okay. So knowing that, this essentially come up to our rule number 4. Means if we were trying to integrate this area under the shear is gonna be equal to bending moment. If we were trying to write this in mathematical way, that would be integration of shear. That's gonna be equal to your m. Those two. Right? Now we're gonna move up to the next rule. For this area we just talked about, if this area is above the x-axis, then that area is considered as positive value. However, if area below the x-axis, this area is going to have a sign of negative. Okay. So next rule, we're going to, if we have a concentrated moment now instead of concentrated force, check on the video on low shear bending analytical 2. That example have our concentrated moment, and I believe the previous video for analytical example 3 has a concentrated moment as well. So when you have concentrated moment, how do we interpret in your graphical approach? Then here's a rule. It's going to be the moment. If you have a concentrated load, the moment is going to be moments jumps upward if it is clockwise rotation. Then on the contrary, moments is gonna jumps downward if it is the moment is counterclockwise rotation. Okay. A lot of rules. So one last thing I want to bring to your attention is from rule number 3 and rule number 4. We already learned in calculus, whenever if this slope if the slope of bending, which means dm over dx, if that equals 0, if slope is 0, in other words, your v will be equal to 0. If v equal to 0, what do you think your bending moment will be? So think about this. If you have a curve here, what is the slope at this point, at the peak? Slope is 0. If slope is equal to 0 for dy over dx, what does that mean? You reach the maximum value of y. So translate it here, which means your m is your maximum of bending. Okay, so that's something to pay attention to. If you have a slope equal to 0, then you will have the highest point or the lowest point, maximum or minimum, right? Because it could be concave down this way. The slope is 0, and that's going to be giving you the minimum value. Okay, so that's all the rules. Now we're going to look at some example in the next video to apply those rules using the same example you did for analytical approach. See you next time. Bye now.